Good morning, everybody. All right, so picking up from the end of the last lecture, we were talking about how floating point numbers are represented on your computer. Right? So the format that we're going to use to discuss floating point numbers, we're going to use base 10 instead of binary. We're always using 4 digits to represent the floating point number. Right? So we have a 3-digit integer here, and we've got a 1-digit integer there. The 3-digit integer is called the significand, right, or just S. Right? We have the restriction that the first digit of the significand is never 0. So the smallest value of S that you can have is 100. Over for the exponent, we want to be able to represent negative exponents, and there's no sign on the digit D4. And so the trick that we play here is to let D4 range in the value from -5 to 4, from 0 to 9, and then we subtract some fixed value, right? And the fixed value that we've chosen is 5. So the total exponent is always between -5 and 4. Right? And if you sketch out, or you just draw out what the some examples of floating point numbers are using this format, you can quickly come up with a table that looks like this. Right, obviously if you wanted to, you could enumerate all of them, but that would take many lines. Right, and so when you do this exercise here, what you quickly realize is that the difference between adjacent floating point values changes with the magnitude of the value. Right, and so here we've got the 2 smallest floating point values that we can represent that are greater than 0. Right, so 100 times 10 to the -5. 101 times 10 to the -5, right? The difference between those values is 10 to the -5, right? It's 1, right, times the exponent here, right, times 10 to that exponent, right? So it's 1 times 10 to the -5, right? If the exponent changes, then the distance between those two values also changes, right? So when the exponent becomes 2, the distance between adjacent floating point values now becomes 100, right? 10 to the 2. And so when you get to the largest floating point values, or the largest exponent that we can use with our format, right? So you end up with values of 1,000,000 and 1,010,000, right? The distance between adjacent floating point values is now 10,000. And so what that's telling you right away is that there are many values that many real numbers that you can't represent exactly in our floating point format. Right? I can't represent any number between 10,000 and 10,100. Right? If someone was to use our floating point format and they wrote down the number 10050, right? When we convert that to our floating point format, we have to convert it to either 10,000 or 10,100. Right? Okay, so that distance between floating point values, right? That value is called the ULP. The unit in the last place, right? It's called the unit in the last place because it's just 1, right? And so the last place is the rightmost digit of the significand, right? And so the unit in the last place, the difference between two floating point values is just 1 times 10 to the -5, right? Or times the exponent, right? So the most of the time, right? When the exponent changes, then the value of the ULP changes, right? Because you're changing orders of magnitude. Okay, so if you were to read any of the floating point literature, please don't interrupt when I'm talking. So if you were to look at the literature that talks about floating point numbers, they'll often talk about the errors measured in ULPs, right? And so this is useful when you're talking about floating point values. So if you're trying to solve some scientific or engineering type problem or mathematical problem that involves real numbers, right? And you're trying to devise some algorithm that computes the value, right? And you want to share your algorithm with the rest of the world, right? Often you'll do some sort of analysis and you'll tell people this thing works up to some number of ULPs of error. So it'll compute some value up to or within some number of ULPs of error. Right? If you need to know what the value of an ULP is for any particular value, you can use the class math and the methods ULP to find out what the value of an ULP is. Right? So java.lang.math.ulp and then 1 will tell you what an ULP is for the value 1.0. So we want to talk about the error between a true value or some value and some computed value, right? So for example, if, again, going back to here, right? If someone was to use our floating point format and write down the number 10001, right? We know that we can't represent that number exactly. So there will be some error between the number that they wrote down and the number that's represented in our floating point system. So the error between two values, there's many ways to calculate it, right? One of them is the absolute error. So the absolute error, you have some quantity x hat, right? So we're just going to call that the true value of the quantity, right? And some other value x, which is the approximate value of the quantity, right? The absolute error between those two values, you just subtract them and take the absolute value, right? The order doesn't matter because you're taking the absolute value, right? So for example, if someone wrote down the number 10001, that would be their true value, right? But their floating point value would just be 10,000, right? And so there would be an error of 1 times 10 to the minus 5 in that case. Sorry, there'd be an error of 1 in that case. Yeah. The absolute error would be measured as 1. Now, we're going to express those in ULPs, right? And so whenever you convert a real value, right, and that real value fits in the range of our floating point type, right, the nearest floating point value to that value that the user is using will have an error of 1/2 ULP. Right. So let's go back to this table here. Right. So let's imagine that we're in this case here, right? So we have the number, so the user writes in the number 10,000 and say 10,002, for example. Right? So they write down 10,002, right? When they write down 10,002, and that gets converted to our floating point format, right? The nearest floating point number is 10,000, right? And so the difference is going to be 10,000 minus 10,002, take the absolute value, right? So that's 2, right? But the 2 is over here, right? It's over in the rightmost digit of the decimal value. We've only got 3 digits in the floating point value, right? So we want to express the error relative to that 0 there, right? And so the error in ULPs in this case is going to be 0.02 in this case, right? Yeah, 0.02. Now, if you were to write down the number 10,050, right, you're halfway between these two values, right? So we convert the 10,050 to either the 10,000 or the 10,100. It doesn't matter in this particular case. So suppose we convert it to 10,000, right? Then the difference between the two values is 50. Oops, sorry, right? So 50, right? We want the error relative to that last 0, right? And so that's 0.5. So that'll be an error of 1/2 an ULP, right? If you're halfway between two numbers, right? Then the error between between your number and the nearest corresponding floating point value is 1/2 of an ULP. So to do these calculations, you need to follow these. You have to follow these 3 rules here. Right? You're going to write down the true value as a floating point value. Right? So you're going to write it down using your 3-digit significand, right, and your exponent. You're going to write the other value, the approximate value, right, as a floating point value. Right? So again, 3-digit significand plus an exponent. Right? But when you do this, you have to make sure that you use the same exponent as the true value. And so I'll show you some examples of this in just a second. Right? Then you go ahead and compute the absolute error. Right? So true value, write it down as best you can using the floating point format. Do the same thing with the other number, but make sure you use the same exponent. Okay, so here's our true value, 1.29. Right? Suppose you calculate some value, right? That's supposed to be 1.29, but you end up getting 1.25, right? What's the error between the two numbers in ULPs, right? So I write down the 1.29 in our floating point format, right? So that's 129 times 10 to the minus 2, right? 3 digits, so 129, right? Pick the exponent so that 129 times 10 to the exponent is equal to 1.29. Do the same thing with the other number, right? So 1.25 is 125, right, times 10 to the minus 2, right? The two numbers have the same exponent, so I can just go ahead and subtract them, right? We subtract them, you get 4 times 10 to the minus 2, right? That exponent is the same as the exponent of the true value, right? And so now we know that that value, so the significand, or just the integer part here, right, is the error in ULPS. Right? And so that gives you 4 ULPS in this case. Right? So once again, take your true number, write it down in floating point format. Take your other number, write it down in the floating point format, but make sure its exponent is the same as the true value. Take the difference, and then the difference after you get rid of the exponent is just the number of ULPS of error. Right, so here's another example. This time, the exponent, when I write down x, is going to be different for x hat. Right, so when I write out 12.1, right, that's 121 times 10 to the minus 1. Right? If I was to write out 0.5 in its floating point format, right, that would be 500 times 10 to the minus 3. Right? Everybody see that? Right? So that's 121 times 10 to the minus 1. Right? That would be 500. Right? 3 digits in the significand, first digit's never 0. Right? So that's 500 times 10 to the minus 3. Right? I don't write down 500 times 10 to the minus 3 here. Right? I make sure the exponent is the same as this one. Right? So in other words, I multiply the exponent, or I raise the exponent to minus 1. That means you have to adjust the significand correspondingly. Right? So that becomes 5 times 10 to the minus 1. Right? Now just do your difference, and you get 116 times 10 to the minus 1. Right? That exponent is the same as that exponent, so that number there is just the number of ULPS. Right? And you have a 116 ULPS of error. Right? Now, if your true value is some real number, right, as opposed to some floating point value, then you just keep all the digits of the true value, right? So you still write it out in your floating point format, but now you're allowed to keep all the extra digits, right? So all the digits after the decimal place. So if I have that number there, right, when I try to write it out in our floating point format, it's 592, right, 3 digits. Now I keep the rest of the digits, so decimal 875603, right? Set the exponent. The important part here is getting this exponent right, right? That's the important part here, right? So the exponent here is times 10 to the 2, right? Now when you write out your second number, you make sure that you write it out also using 10 to the 2 as the exponent, right? So that's 589. Take your difference, and that's 3 point something, right? That exponent is the same as the true value exponent, so that's just the number of ULPS. Right? I'm only going to say this, I'm only going to talk about this on this slide. Sometimes you want to compute the relative error, right? So if you've done any science, any of your science courses, you might have been taught about the relative error, right? The relative error is just the absolute error divided by the true value, right? So it's the error in percent. If you're computing a relative error, you always use real arithmetic to compute the relative error. So you don't do this in terms of ULPS normally, right? And so that's how you can compute relative error if you need to. I'm probably not going to ask you to do it. So that's how to compute the error between two values. Now, once you've got your floating point numbers, you probably want to do some arithmetic with them. Right? We're not going to talk about division or multiplication because those get relatively complicated. Right? But it is useful to look at how the floating point representation affects addition and subtraction. Right? So if you want to add two floating point values, right, then you write out floating point values in our floating point format. Right? So 12.1 becomes 121 times 10 to the minus 1. Right? 63.8, 638 times 10 to the minus 1. Right? Again, the goal is to make sure that the exponents are the same, right? Because now all the digits over here line up when you add them up together, right? And now just go ahead and add using whatever algorithm you want to add the two numbers, right? So here you get 759 times 10 to the minus 1, right? Or 75.9. Say a similar example here with larger values, right? 81,500, 815 times 10 to the 2. Right? 13,600, well, that's just 136 times 10 to the 2. Exponents are the same, right? Again, that's what you're looking for. Go ahead and compute your sum, you get 951 times 10 to the 2, right? Now, notice that in the answers so far, right, our significands always have 3 digits in them. So that's good, because we can represent those numbers in our floating point format. Right? Now, what happens if the answer does not have 3 digits? In particular, what happens if it has more than 3? Right? So if the result produces an extra digit, you've got a problem. Right? So when I do 82.1 and add that to 63.8, right, you get 1459 times 10 to the minus 1. Right? There's 4 digits in that significand. Right? Our format doesn't let you use 4 digits. It only has 3. Right? So what happens? Right? And so on an actual computer, a few different things could happen. Right? So it might round that to 3 digits. Right? So when it rounds 1459, right, it rounds it to 1460. Right, and keeps the first 3 digits. So that's 146 times 10 to the 0, right? Depending on who designed your computer, your computer CPU, right, they may not round it, they might just drop the 4th digit, right? So if you just drop the 4th digit, you end up with 145 times 10 to the minus 1. 1450 times 10 to the minus 1, and then you convert it to 146 times 10 to the 0, right? So for our purposes, we're always going to round, right? So there's lots of ways you can think about this. You can write this as 145.9 times 10 to the minus 1, right? Then round, so that's 146. Sorry, 145.9 times 10 to the 0, right? Then round it to 146. Another example, so if you add these two numbers, you end up with a 4th digit, right? So 1751 times 10 to the 2, right? I guess multiply or increase the exponent by 1 and shift this decimal place 1 to the left to get 175.1 times 10 to the 3. Round, and you get 175 times 10 to the 3. Right? So the fact that you've got, the fact that the sum produces an extra digit, right, requires you to do something to convert the intermediate result to some value that you can actually represent in your floating point format. Right? Notice that the answer is incorrect, right, if you compare it to the true mathematical answer, right? This really should be 145.9, right? But you can't represent 145.9, right? So now you've got 146, right? And now your calculated answer, right, differs from the true answer, right? So you can't even do a simple sum in floating point and be guaranteed to get the correct result, right? If the sum produces an extra digit that your floating point format can't hold, you lose some information regarding that extra digit. Now what happens if the two numbers have very different exponents? Right? And so the 2 digits have very different exponents. You take the larger number and you write it out in your floating point format. Right? So 4,320,000 and 12.1. Take the bigger number, the number whose magnitude is larger, right? So you take that one, it becomes 432 times 10 to the 4, right? Now when you write out your second number, you also want to use the exponent 10 to the 4, right? So 12.1, if I try to write that out as something times 10 to the 4 is 0.00121 times 10 to the 4, right? Now you add the two numbers, right? So you get 432.00121 times 10 to the 4, right? I can only use 3 digits in our floating point format, so I'm stuck with 432 times 10 to the 4, right? So I lose the 00121 in this case, right? And that's my final answer, right? So notice that when you try to add these two numbers, right, you actually need 8 digits to actually compute the sum, right? I need all 8 of these digits here to get the correct sum. My floating point format's only got 3, right? And so we end up with this problem when you try to get the final value, right? And so notice what's happened here, right? I've got x and y, right? So I do x plus y, right? And what's the answer? The answer is x, but y is not 0, right? So you end up in the situation where x plus y equals x, where y is not equal to 0, which mathematically makes no sense, right? But that's what happens in floating point when you do floating point arithmetic, right? If you add numbers of very different magnitudes, right, you're going to lose a lot of information regarding the smaller value. Yeah?
How does our code actually, I guess, calculate? Because assuming that it is just made out of 3 digits,
Yeah.
so do they calculate the intermediate result somehow by
No.
allocating more, or is it just...
Well, so the answer is complicated. I'm going to get to that in a second.
Okay.
Right. So the question has raised the issue, right? How exactly do you compute this thing, right? I need the 8 digits here to calculate the intermediate result. Can I actually do it with 8 digits, right? And if I were to say yes, you would say, well, why isn't our floating point format using 8 digits then? You've got 8 digits. And so the answer is, especially in the past, so in the early days of computing, right, sticking in these extra digits in hardware was not feasible, right? So if you had an 8-bit computer back in the 70s or something like that, right, it was not, either it wasn't easy to do or it was prohibitively expensive to do, to stick in some extra digits so that you can compute floating point sums correctly, right? So using extra digits was not always feasible in computer hardware, right? Now, on a modern CPU, this is less true, right? So modern CPUs do use extra digits to compute when they work with floating point values, right? But back in the day, that wasn't the case, right? So if you don't have any extra digits, right, and then there's no way to keep this 0, 0, 1, 2, 1, right? So if we don't have any extra digits, you're stuck with just adding 0, right? So throw away the 0.00121, right, when you write down y, right? And now you get, now obviously you add 432 and 0, right? And so again, you get x plus y equals x, where y is not equal to 0. Right? So that produces the same result as on the previous slide, right? No extra digits, throw everything away after the decimal point, and just go ahead and compute the sum, right? And so what does that tell you? It means you can't compute that sum in our format correctly. In fact, you can't even compute it at all, right? You end up with the original value. You end up with the first value. All right, so if you don't have any extra digits, then floating point arithmetic becomes very, very inaccurate, right? So it becomes extraordinarily inaccurate. So I have the values 10.5. I would like to subtract 9.98, right? Subtraction works the exact same way as addition. Take the 10.5, right? That becomes 105 times 10 to the minus 1, right? Write out the 9.98 in your floating point format, but make sure the exponent is the same as the larger of the two values, right? So 10.5 is greater than 9.98. So when I write out 9.98, I want to use 10 to the minus 1 as my exponent, right? No extra digits, so when I write it out, it's 99.8. So you throw away the 0.8, right? Now compute the difference, right? So that's just 6 times 10 to the minus 1, right? Now, when you take the 6 times 10 to the minus 1, right? So that's our new intermediate result, because our significand is not allowed to have a 0 in the front, right? So I have to scale that up to 600 times 10 to the minus 3, right? If you compute the true result, right, the true result is 0.52, right, which all of you should be able to do in your head, right, or at least by scribbling it down on a piece of paper, right? So if you compute the difference between the 600 and the 520, right, that's 80, right? So you've subtracted two values, right, and you have an error of 80 ULPs. The standard for floating point numbers says that if you do basic arithmetic with two floating point values, right, so addition, subtraction, multiplication, or division, right, the final result must be within half an ULP of the true answer, right? And that's 80 ULPs off, right? So we're off by a factor of 160, right? More than 2 orders of magnitude, which is enormous for floating point numbers, right? So that's unacceptable. So we need some way to fix the problem, right? So the solution is to insert extra digits, right? Now, you can't insert an extra, in hardware, you cannot insert an arbitrary number of extra digits because you don't have the physical hardware to do so, right? In software, you can, but then your floating point calculations become extremely slow, right? So if you were to compute floating point in software, which is possible to do, right? That's much, much slower than having your CPU do it. So if the CPU manufacturer can do so, right, they will insert extra digits. So these extra digits are called guard digits, right? So suppose they were able to insert one extra digit. What does that get you? Right, so I'm allowed to use one digit after the decimal place now. Right, so 10.5 is still 105 times 10 to the minus 1. Right? Now when I write out 9.98 though, I can write that out as 99.8. Right? So that lets me keep that decimal, the digit after the decimal point. Right? Now do your difference and you get 5.2 times 10 to the minus 1. Right? I'm allowed to keep that extra digit after the decimal point. Right? Now when I scale this up to our floating point format, right, I get 520 times 10 to the minus 3, which matches the true result. Right? So it looks like inserting one extra digit gets you, well in this case it gets us the exact result, but does it get us to within half an ULP every time? Right? And it turns out the answer is no, not for addition or subtraction. Right? So for addition or subtraction, right, you need at least 2 guard digits if you're working in base 10. Right? So 110 minus 8.59. So 110 is the larger of the two values. So that's 110 times 10 to the 0. Right? 8.59, the magnitude is smaller than the 110, so I make sure when I write this out, the exponent is 10 to the 0. Right? So that's 8.5 times 10 to the 0. Right? Do your difference and you get 101.5. Now here's the problem, right? So you have an intermediate result that has 4 digits again. Right? And so now you're stuck again, right? I have to convert that intermediate result to 3 digits. So in this case, I'm going to round, right? So I'm going to round the result and go to 102, right? On some computers, you might truncate or lose the digit and end up with 100. It doesn't matter what you do in this course. I don't care if you normalize it around, right? So we're going to round because that actually makes the situation slightly better, right? And you end 102 times 10 to the 0. Right, the true value, if you do this difference, is 101.41. Right? And so you end up with almost 0.6 of an ULP error, which is slightly too large for the IEEE format. Right? So it turns out you need 2 guard digits. If you were to do the exercise using 2 guard digits, you would end up with a result that actually gets you to within half ULP of error. Okay. So when you subtract 2 floating point values, you end up with this phenomenon called, well, not just floating point values. If you subtract 2 numbers in any base, right, you end up canceling digits in the final result, right? So you end up with what's called cancellation or loss of significance, right? And this is just how subtraction works, right? How differences work. So here I've got 2 numbers. They have 10 digits in them, right? So I'm going to temporarily switch to a 10-digit format, right? The first digit ends in 90. The first number ends in 90. The second number is the same as the first number, except it ends in 89, right? So that means their magnitudes are very similar. If I subtract these 2 values, right, obviously you get 1, right? So notice what's happened here, right? I had 10 digits in that second number. Right, 10 significant digits in the second number. I've got 1 significant digit in the final result, right? And so I've lost 9 digits of significance compared between the x and y and the difference of x and y, right? Obviously, this is not surprising, right? This is how subtraction works, right? The digits over here, right? So in your floating point number, the leftmost digits, those are called the most significant digits. Right? They're the most significant ones because they're the ones that contribute most to the magnitude of the number. Right? That 1 matters a whole lot, that 1 matters a whole lot more to that 9 for the overall value of that number. Right? So the leftmost digits are the most significant digits, the rightmost digits are the least significant digits. Right? When you subtract 2 numbers, you get cancellation because the leftmost digits, right, the most significant ones, cancel one another out, leaving you only with the least significant digits, right? Again, this is just how subtraction works, right? So cancellation is simply a consequence of the way that subtraction is performed, right? Now, if you're subtracting 2 numbers and the numbers are exact, right, then you don't care, right? You compute the difference and that's your answer, right? So that's called benign cancellation, right? Benign meaning there's no unfortunate side effects. Right? There's something called catastrophic cancellation that occurs when one or both of the values that you're using, they actually contain some error. Right? So for example, if I try to compute some difference, right? But when I compute the difference, the two values that I'm subtracting, those values are also computed in floating point. Right? Because you've already seen, right, when you compute something in floating point, there's usually some small amount of error in the computed result. Right? So suppose I compute b squared minus 4ac, right? So that's the value underneath the square root in your quadratic equation. I'm going to pick numbers that actually fit in our floating point format, right? So b is going to be 3.34, right? A is going to be 1.22, and c is going to be 2.28, right? So you just go ahead and compute this using regular arithmetic, right? So not using floating point. So when I do this regular arithmetic, right, I end up with 0.0292, right? If I write that out in floating point, that's 292 times 10 to the minus 4, right? So this is not with floating point, right? This is using real math. Okay, so what happens if I compute this in floating point, right? Now, we don't know how to multiply numbers in floating point, right? So I haven't told you how you compute b squared or 4 times a times c, right? So for the purposes of this slide, let's just assume that when I compute these, I'm just going to compute them using real math and then round the result to the nearest floating point value, right? So in other words, I'm going to try to make this the best case error possible, right? Because it's when the computer actually multiplies these numbers out, it's probably not going to be able to keep 6 digits to compute the product. Right? So let's multiply out b squared. So that's just 11.1556, right, which is 111.556 times 10 to the minus 1. Right? So I can't keep these 3 digits after the decimal point, so I'm going to round to get 112. Right? For AC, it turns out it's 111 when you get down to 3 digits of significance. Right? Okay. That exponent is the same as that exponent, so I can just take 112 and subtract 111 to get 1 times 10 to the minus 1, right? Convert that to that to our correct floating point format, right? So that's 100 times 10 to the minus 3. Notice what's happened, right? We got a 1, a 0, and a 0 in the significand. We got a 2 and a 9 and a 2 in the true significand. Our exponent is minus 3. Right? Here the exponent is minus 4, right? None of the computed digits are right, right? And this calculation was not particularly long, right? We multiplied 2 numbers, multiplied 3 numbers, took their difference, right? And the answer is completely wrong, right? So if you compute the error between the true value, right? So back here, 292 times 10 to the minus 4, right? And the computed value, which was 100, times 10 to the minus 3, right? Make the minus 3 a minus 4 in the second number, so that becomes 1,000, right? Subtract those two values, that's 708 ALPS, right? Which is enormous. Right? Again, remember the standard for floating point numbers said that value should have been computed to half an ALP, right? This value here should have been computed, well, the 4a should be computed to half an ALP, right? Then that times c should be computed to within half an ALP. And then the difference should be computed to within a half an ALP. Right? Even if you do all that, right, there's no guarantee that the b squared minus 4ac is anywhere near 1/2 an ALP of an error. Right? And so this phenomenon is called catastrophic cancellation. Right? You've subtracted 2 numbers that are close in magnitude, but both of those numbers had some error in them. When you do so, the cancellation doesn't work the way it should if you actually had the true values. Right? So that's a very big error. Now, if you want to, you can read that floating point error notebook. I'm not going to ask you to do this, right? So for those of you who are curious about how all of this works, right, in the floating point error notebook, there are some examples where you actually compute something that involves catastrophic cancellation, right? And then the notebook says, look, for this particular thing that you're calculating, there's a way to transform the equation to remove the difference, right? Or to move the difference somewhere else so that catastrophic cancellation doesn't occur, right? Now, when you can actually do this, it's very rare that you can actually do this, right? And so if you read the notebooks, you'll see there are some equations that don't look that they would be very practical for any ordinary purpose, right? But if you're clever, you can rearrange or rewrite the equations in some way so that you can avoid catastrophic cancellation, right? So see the floating point error notebook if you're curious. All right, so what about something a little more relevant to a computing science student, right? So every basic floating point arithmetic operation, when you perform that calculation, there is the possibility that you end up off by 1/2 an ULP, right? If you have to repeat this calculation over and over and over again, right, that 1/2 an ULP error can accumulate over and over and over and over again, right? So for example, if you add 100 numbers, right, each sum has 1/2 an ULP in error. After you add the 100 numbers, you might end up with 50 ULPs of error in the final result, right? So what is a common situation where you add or subtract lots and lots and lots of values? Well, if you're computing an average, that involves summing a bunch of values, right? If you're computing any sort of basic statistic, typically that ends up involving a sum of values, right? So if you wanted to compute a standard deviation or a variance, you're summing a bunch of values, right? If you're summing lots of them, you can run into this. You can run into the problem where the final calculated result has a lot of error in it, right? So here's an example in Java. Right? I'm going to sum 1,001 floating point numbers. Right? I'm using float in this example because float has a fewer number of digits than double, so it's easier to show you it's easier to produce a large difference, a large error with float than it is to use double. So I'm going to start out with 1,001 floating point values, and I'm going to stick in the number 0.1, right? So I'm going to so I have 1,001 0.1 values, right? And then I'm going to set the first value to 1 million, right? So in other words, I'm going to take 1 million plus 0.1, and I'm going to add 1,000 0.1s, right? So 1,000 times 0.1 is 100, right? 100 plus 1 million is 1,100,000. Right? If you sum those values using float in Java or any other computer that's using a 32-bit floating point number, right? You end up with the value 1,125,000, right? You can't even sum 1,000 numbers correctly to get the right sum, right? You're off by 25 in the final sum, right? And these numbers aren't even particularly large, right? That's 1 million, that's 0.1, right? The problem is the reason this occurs is because the magnitude of these two numbers, it's very different, right? So imagine what this sum actually looks like, right? You start out with 1 million, and then you add 0.1, right? And you know what happens when you add a small number to a large number, right? You lose part of the small number, right? So after adding 0.1, you get 1 million point something, but the something's not 1 anymore, right? And now you add 0.1 again, right? Well, basically you're adding 0.1 to 1 million again. So you're going to lose part of the 0.1 again, right? And this happens over and over and over and over again until you sum all the values, right? Now, if I put that 1 million at the end of the array instead, right? So in other words, if I just change that one line and write the million at the other end, that actually prints out 1,100,000, right? So the sum is computed as accurately as you can in this particular case, right? Why does this happen? Because now you sum 0.1 and 0.1. They have the same magnitude. So the sum, when you compute it, is probably very close to 0.2, right? 0.2 plus 0.1, well, they have the same magnitude. So when you add the 0.2 and 0.1, it's probably very close to 0.3, right? And so on and so on and so on, right? And so now you're summing the values, and the values have been sorted by their magnitude, right? It's not till the end when you take the 100 and add that to the 1 million, right, where you run into any significant round-off error, right? Okay, so if you're summing many values, and this happens a lot, right, and you realize that the sum that you're computing is not correct, right? You might go and ask somebody, hey, how do I fix this problem, right? I can't even sum these values correctly, right? If you go on the internet and search for this, you'll often see people recommend, well, you should sort your values before you sum them, right? So sorting them, the idea is maybe I can keep the values with similar magnitudes close together so that when I add them together, I get the smallest error possible. Right? The reason you don't want to do this is because, right, you may not want to change the order of the values in the array or the list that you're summing, right? That array or list might be important to you. The order might be significant, and you don't want to reorder it by sorting it. You could copy it and then sort the copy, right? But now you've doubled the amount of memory that you needed to use. Right? Okay, so the other problem is sorting is in complexity class n log n, right? But if you sum n values, right, you should be able to do that in O(n) time. Right? So if you sort then sum, right, you now are in the situation where you've done an n log n calculation followed by an O(n) calculation. Right? Whereas summing should just take O(n). Right? And so I guess the question is can you actually sum these values without sorting and still get the answer that is as accurate as possible, or as accurate as if you had sorted it instead? The answer is yes. So again, I'm not going to go over the details of this algorithm. It's in the floating point error notebook if you want to see it. Right? So this is called Kahan's algorithm. So someone did figure out how to do this as accurately as possible. Kahan is one of the principal architects of the IEEE 754 standard. He's a Canadian computer scientist. So he was at U of T, I believe. I think. But he is a Canadian computer scientist. He won a Turing Award in part for his work on the standard and for numerical analysis. All right, so I think this is a good place to stop. So instead of starting the next lecture, we'll stop here. Your assignment is due today, but you have until Monday to finish it, right? Oh, there's one thing. So someone did ask me, I forgot to tell you how to do this. If you're still working on the assignment and you haven't figured out, hey, where the heck is my file that I want to submit, right? You can always figure out where your file is in Eclipse by asking Eclipse, right? Okay, so imagine I want to know where is bouncing-ball.java found on my computer, right? So in Eclipse, you just select the file, right? Then in File, you go to, in File, you go to Properties, right? When you click Properties, it'll tell you where's the location of the file on your computer. And, wait, it gets better. There's a button way over here, right? If you press the button, it will open up on a Mac your Finder. On Windows, it'll open up File Explorer, and it'll open up in the directory that contains the file, right? Now just drag this file over to OnQ. Don't move it, right? So don't move it on your file system. Eclipse wants to manage your files for you. So either copy it and put it somewhere else, or drag it into OnQ when you go to submit it, and that's the correct file to submit. After you submit, make sure you check on OnQ that the file you submitted is the one you wanted to, because every year there's like a dozen students who end up submitting the wrong version of the file. So it's either empty, or it's an incomplete version, or it was an unsaved version, and then you end up getting 0 on the assignment. Right? So always double check your files after you submit them on OnQ. All right, so we're done. I'll see you next week.